you very much, Leah. It's a pleasure to be giving this webinar today. I should say that I'm also one of the co-directors for the Institute for Molecular Science and Engineering, and so through the talk I will try and illustrate where I see some of the strengths of this joint approach between molecular science and engineering lie, and how they can help to develop better processes. And I'm also director of the Center for Process Systems Engineering, which looks at developing systematic computer-based approaches for design and operation of manufacturing processes. So this comes neatly together in this webinar. We try to develop this concept of molecular systems engineering, in which we root ourselves in the study of functional materials at the molecular level, things like polymers, crystals, macroemulsions, and so on, and develop fundamental understanding and tools. And I will show an example of this in this talk. So things like perturbation theories or molecular simulations. Then we try to go beyond the molecular scale to the scale of systems, where we take a product and process-centered view and develop generic methods, automated algorithms that can be applied again and again to different settings, and to develop multiscale approaches, to develop models across the scales, interfaces between those, so that we can join the molecular scale to the much larger scale of actual manufacturing systems. And the engineering aspect of this is we want to focus on industrially and societal problems, and we want to focus on making those systems, man-made systems, better. So we want to go beyond understanding them and beyond modeling them to actually designing them and operating them better. And hopefully these themes will come through the talk. So what I'm hoping to do this afternoon is to, first of all, convince you that we need to look at the molecular scale even when we're designing manufacturing processes. And Leah mentioned that this series is in the context of our work on greener plastics and generally more sustainable materials. What I will be talking about here is the processes through which we make different materials. I won't be focusing specifically on plastics because that's a problem we haven't addressed yet, but the techniques that we've been developing for other manufacturing contexts, for example, pharmaceuticals, should be applicable to plastics, and that's what we're hoping to find out through this new activity in greener plastics. So one of the key tools that I will be using is computer-aided molecular and process design. That's quite a mouthful, and so I'll use CAMPD for short. And I will first show you a property prediction platform which we have developed that helps us to connect to the molecular scale in a predictive way. And then I will show you some examples of these different integrated molecular and process design problems, just to try and illustrate both some of the benefits of taking an integrated approach, as well as some of the research challenges. And we look at a number of different things. So we look at crystallization, we look at waste heat recovery through organic Rankine cycles, and we look at solving or making reactions better through solvent design, and then end with some conclusions. So why is it important to integrate the details of the molecular scale with the much larger scale of a process like a distillation column or reactor and so on? So you have to remember that when we develop a manufacturing process, what we're trying to do is to make a particular product of a certain quality, and we're trying to do that while doing it safely, while minimizing the environmental impact of that manufacturing process, and also while minimizing the cost of manufacturing, which comes both from our capital investment cost as well as our operating costs, so things like energy costs, for example. And of course, energy, if we can reduce the amount of energy we're using, that has both environmental benefits as well as economic benefits. So let me try and explain in the context of solvents, which is an area we've worked a lot on, why this is important. So you use solvents in many ways in manufacturing processes, and you use them, for example, for crystallization, so to separate your valuable product from the rest of what comes out of the reactor and obtain a nice pure crystal. So paracetamol, for example, is a product that you consume in crystalline form. And you might dissolve paracetamol in acetone, which is pure acetone here. It's fairly soluble in acetone, or in water, and it's hardly soluble in water. But if you take a mixture of acetone and water, for example, a 50-50 mixture, you have a much greater solubility than in either acetone or water. So being able to figure out that this mixture behaves so much better and gives you greater solubility means that you can use less solvent to dissolve a certain amount of paracetamol. You can have a smaller crystallizer, and you can therefore reduce cost, the environmental risks of using solvent and the safety risks of using solvents. So you can reduce your energy consumption. So if you can figure out that you have this behavior and under what condition it happens, that can have huge benefits for your manufacturing process. Solvents are used widely in making pharmaceuticals, and so that comes with a lot of implications. The choice of solvent, of course, impacts the process performance, but it also impacts the way that your crystal looks. And so, for example, you can get needles in certain solvents, and those can then be difficult to process further and to turn into the product that you really want. So that can be a limitation. And of course, solvents can pose safety risks. In the pharmaceutical industry, solvents have been found to be responsible for 50% of greenhouse gas emissions in the industry. So through the cost of solvent recovery, for example, and solvent disposal. So it's really a major environmental impact. And as I've said, they impact on equipment, impact on other properties like the viscosity, and therefore how easy it is to get or difficult to get your fluids around the process. So choosing a solvent, you need to address all of these aspects to find the best solvent for your process, right? There is no such thing as a good solvent on its own. It depends on how you're using it in context. So how might you go about this? Well, one fairly obvious way to go about this is to try and look at the properties of the solvent and to try and identify the properties that really matter for the performance, because that's reasonably intuitive and you can derive this from physical insight. So if I look at the example I've got here, which is carbon dioxide capture by chemisorption, so I'm looking for a solvent that is going to be absorbing carbon dioxide preferentially, so it's going to have a high affinity for carbon dioxide. So I can absorb it from a stream, for example, of natural gas, or perhaps a flue gas from a power station. So that's really important, but I also need to then be able to separate the CO2 from the solvent. And so when I want to have high affinity, I want the separation to be easy and to have low energy. So there's a big trade-off here. And I can see that the properties that matter for this include things like the molar volume, the vapor pressure, the heat capacity. And so what I've done here is I've got a number of putative solvents. These are just code names for these possible solvents. And I'm comparing them to monoethanolamine, which is a standard solvent for CO2 capture. And when you see a red bar, it means the solvent is worse than monoethanolamine. And if you see a blue bar, then it is better than monoethanolamine. So for example, surface tension here, when the solvent is better, it means that I may need a smaller column to effect the separation, which is good, less capital cost. On the right here, I've got other metrics, and these are environmental health and safety metrics. So you can see all of these solvents do better than monoethanolamine. From this perspective, this is the cumulative energy demand. This is the global warming potential, you see mixed performance, and this is an eco indicator. So you can see that it's not very clear, the picture that emerges from looking at the properties. And the reason that is because the properties are not the end of the story. They don't really tell me about overall process performance. I don't know from these whether I'm going to need a very large distillation column or I'm going to have very high energy demand and so on. I need to be able to quantify this. And I can only quantify this if I move to a process model and I really look at the use of the solvent beyond the properties in the process. So this is where the role of integration comes in. Okay. The other thing about properties is that having better properties doesn't necessarily mean we have a better process. So this is an example here that from a study we did of a reverse osmosis plant where we were trying to desalinate water, and we were looking at multiple stages of membranes. So we have these membrane modules, and we were looking at making the membranes better. And what you find is shown here, the cost of the water per barrel versus the relative permeance of the membrane. So the larger the number, the better the membrane. As you can see, as you improve the membrane, initially the cost drops off rapidly. This is the total cost in yellow. But then this tapers off. And yes, it continues going down, but the improvements are not so significant. And there are other bottlenecks in the process that can then help you to reduce the cost. And so you might look, for example, at the details of the fluid flow over the membrane to remove the concentration gradients that are causing the performance not to improve so much here. And so, yes, up to a point we should improve the properties, but at some point it's wasted effort, essentially. And so we really need to look at the whole process to be able to understand when properties matter. And so what we want to do is to develop tools that help us to make molecular level decisions an integral part of process synthesis and design. And there are a number of research challenges if we want to do this. And this is my summary of what those are. So first of all, you need to have meaningful metrics that you can quantify. And so, as I've said, properties are useful up to a point only, and we often need to try and find something more meaningful than that. You need to deal with the complexity of looking for molecules that are going to work in your process. So for example, if you find a solvent which happens to be actually a gas at the process conditions, then that's not going to work as a solvent at all. Or indeed, if it's a solid, it's not going to work as a solvent. And so you need to have methods that are adaptive enough that they can recognize what will work and what will not work. And this is quite challenging from a numerical perspective and algorithmic perspective. You need to have prediction methods, property prediction methods that are going to help you to assess how well a given molecule works for a given purpose. And so we need to have tools that are accurate enough and fast enough, efficient enough to be able to be used in the context of this integrated design. And that is a challenge to make sure that we can predict all of the properties that we need. Often we don't have everything we need. And finally, and this is something I won't really touch upon today, we need to be able to understand the impact of uncertainty. So in all of the models that we develop, there will be some uncertainty. And again, as for the properties, sometimes it will matter and sometimes it will not have an impact on what we are computing. And we need to understand what that impact is. But I won't go into these more advanced topics today. Okay, so I'm going to show you a few equations here, really to give you a flavor for how we tackle these problems and how we translate what I've been talking about into a mathematical formulation, an optimization problem, which is a mixed integer nonlinear problem. So that's a standard kind of class of problems. And so we have a bunch of equations and variables, and I'm just going to highlight the physical meaning of these equations. So we have an objective function, which can be just one function or several functions. So for example, it could be minimizing the total cost, it could be minimizing the environmental impact, it could be minimizing energy consumption, and we can have several of those. We have some equations which are our understanding, capture our understanding of a physical system. So there are process and property models. What happens if I make the temperature larger? What happens if I make the pressure lower? What happens if I change the solvent? How much will be our product flow rate? What will be the quality, the purity of the product, and so on? These are the equations that capture this understanding. We have some inequality constraints, which are design constraints. They're, for example, the purity of the product, the maximum temperature that we want to use in the reactor. Those constraints that make sure that our solvent is liquid at the operating conditions, so bound on the melting point, or for example, on the viscosity of the solvent. And then here we have our variables. So we have some continuous variables that can take any value between a lower bound and an upper bound. So that's the case for temperature, for example. But also we have some discrete variables that can only be 0, 1, 2, 3, and so on, which describe the structure of the molecules that we have in the process. So this is the additional decision that we're making. So for example, if we want to make a solvent, we could build it from atom groups, a CH3 group, 2 CH2 group, and 1 OH group. And that will give us some propanol. right now. So we can build different solvents, different molecules by changing the number of groups of each type. So 1 CH3, 2 CH2s, 1 OH gives us propanol, and these are these N values. That's what this represents. So I'm going to use this throughout the talk, and I'm going to start off by talking a little bit about our property prediction platform, which is really a core to being able to formulate these optimization problems. Before I do this, I just want to say one more thing about the optimization problem. We're using optimization as a mathematical tool. That means that we don't have to try every possibility. So optimization algorithms will help us to search through all the possible values of n and x, and to hone in onto the best possible values based on all these constraints and the objective functions, without having to evaluate everything. And that's really important because the problems very quickly become too large to handle if we were to try to evaluate everything, partly because of the continuous variables that can take on any values between lower and upper bounds. Okay, so a couple of key messages when we come about to talk about the property prediction platform. So our aim here is to predict the thermodynamics of mixtures and compounds for which no data have been measured, so that we can really innovate in terms of manufacturing processes and do better than what has been done traditionally. And the other key here is that achieving the kinds of predictive models that are useful for process and molecular design is not possible without collaboration between physical chemists who really understand the details of the molecular interactions and the engineers who understand why we need those models and what we need to do with them, because that helps us to place a focus on which properties are important and what kind of transferability we have. So this is really one of the fundamental aspects of what IMSE as an institute is about, facilitating those collaborations so that we can have better tools to help us improve chemical and molecular systems. So the model that we've been developing is an equation of state to predict thermodynamics of fluids. So its name is initially the SAFT VR square well, so again quite a long name, equation of state, which was an equation of state developed in the 90s to model systems such as polymers. So where you can go from something like ethane all the way to polyethylene within the same framework, and really take into account the impact of that molecular aspect ratio. And then the other thing is this equation of state is very good when you have a hydrogen bonding system. So you can add little sticky sites here and there to mean hydrogen bonding. And so it has the ability to model systems that improve these kinds of behavior well, while being essentially an analytical equation of state, so extremely fast to evaluate. And of course, that's very important if we want to evaluate many possibilities and different molecules. What we've done through our collaboration is to make this approach more predictive. So initially, it was applicable to a single molecule or a family of molecules, a homologous series like the alkanes, for example. And we've made it more predictive by breaking down those spheres into spheres that correspond to atom groups. So here I'm just saying CH3 and CH2, but you can have OH, COH, and so on and so forth. And we also went and tweaked the details of the theory. So here we have square well interactions between the segments, the little spheres. We changed that to me interaction, so a generalized Lennard-Jones potential. And that sounds like a very small detail, but actually it turned out to be very important to get both the phase equilibria and the caloric properties with the same model, so things like heat capacity. And heat capacity is extremely important when you're doing process design, because this is what determines your energy cost. And so with the phase equilibria, you can know how much of the product you're getting, or how good your separation is, and what is the purity of your streams. And with the caloric properties, you can figure out your energy requirements. And that combination is what enables you to do integrated design. And so, for example, with the more accurate approach, you can use here, this is a mixture of CO2 and methane, and this is the vapor liquid equilibrium of this mixture over a range of temperatures. But you can then take this approach here and play molecular Lego. So you can do CO2 and propane and CO2 and decane, and you use exactly the same models in those two graphs. The only difference being the number of CH2 groups which you put in to your mixture to say you have propane or decane. Okay, so that gives you great transferability. And you can use the same approach with slightly larger number of groups to do things like to predict the solubility of ketoprofen or ibuprofen, this ibuprofen shown here, in acetone in different solvents. So you going from vapor-liquid equilibrium to solid-liquid equilibrium with completely different types of compounds without using any of the solubility data. And so over the years, we've been developing a matrix of group-group interactions. So for example, CH2 with CH3 here, and you have many different parameters that we can use to play this molecular Lego and predict the behavior of mixtures under different conditions of temperatures, pressures, and composition. So let me now show you how we can use this equation of state for computer-aided molecular and process design. And I'm going to start doing this by looking at the design of crystallization solvents. So the key message from this particular application is that we have some strong interactions between the solvent and process variables. So this is what I was telling you at the beginning and why we need to be able to treat the problem in an integrated fashion, but this will really illustrate this point. We're going to be designing mixtures of solvents, so that makes the space of possibilities much bigger because we have to determine the composition of that solvent. And we are not going to be creating new molecules here. We're just going to use solvents from a predefined list. Okay? I will come to the creation of new molecules a bit later. So conventionally, how would you choose a solvent for a crystallization process? So you would choose a crystallization technique. So you might say, I'm going to run a cooling crystallization. So I have my the product I want to crystallize dissolved in some solvent, and I'm going to drop the temperature and it will crystallize out. Something you know, for example, if you have sugar, a lot of sugar dissolved in a solution, and if you let it cool, some of it will crystallize out. Or you might say, I'm going to use an anti-solvent crystallization. I'm going to keep the temperature constant, but I'm going to add another component, an anti-solvent, to the mixture, to the crystallizer, and this will force my compound to drop out and crystallize. Having done this, you would then decide on the operating conditions, so the operating temperature, and you would then dissolve your active pharmaceutical ingredient, the API, in a pure solvent. And then you would choose which pure solvent you have. So you would do things like finding a solvent or an anti-solvent by trying to optimize key performance indicators, for example, the crystal yield or the solvent you use. So how much of the API you have in your solvent initially are you able to crystallize out? Because there will be some residual left in the solvent. And you might want, from an environmental and cost perspective, to minimize the amount of solvent that you use. Okay. Now, by doing this and one decision at a time, you may find that you don't have a very high-performing process, and that you are limited in what crystal yield and solvent use you can achieve. So we're going to see that is how that is the case if we do look at this sequential approach. So, for example, if you just fix the operating temperature, so what I'm showing on this plot is the coefficient of temperature coefficient of solubility. So how much does solubility vary with temperature, which is important if you're doing cooling crystallization, because you want to cool from one temperature to another and get a lot of change in the solubility, so you get this crystallization. So this quantity as a function of the solvent boiling point. So these are different solvents, each dot is a different solvent, and you can see there isn't much correlation here. Between the boiling point and this temperature coefficient. But if we fix the operating temperature, so for example, if we fix it here, then we are going to have a range of points here which are not going to be working for our process. Okay, and we have some points here that are indeed feasible. And so the solvent that is going to have the largest temperature coefficient, which is what we're looking for good crystallization, is going to be this solvent here. So we won't be able to access this solvent there or that one. So we have a missed opportunity because we have fixed the temperature. If we allow the temperature to vary, then we're opening up the field of possibilities, and we can find what is truly our best operating temperature, which is the starting, the higher temperature here. Okay. So we do want to allow variation of the process conditions together with the solvents themselves, the molecular decisions and the process decisions. So we want to make simultaneously a number of decisions. At what temperature should we operate? Which solvent molecule should we be using? And what is the composition of the solvent? Okay, and we've been developing a methodology to do this. So this is your starting crystallizer, where you've got a certain amount of API dissolved in your initial solvent mixture at an initial composition, and all of these need to be determined. We don't know what those numbers are. And then we can, if we want, add a certain number of moles of anti-solvent, and this will cause, and we can change the temperature here to T, and this will cause the crystallization to occur. And so we formulate this, we capture this in those equations that go into our MINLP formulation I mentioned earlier. And we try to solve the problem to look at things like minimizing solvent use or maximizing the yield. Okay, and so let me show you an example of this on the crystallization of ibuprofen, right? So a well-known painkiller. And we're going to use a small list of solvents here. So water, 2 different N-alkanes, 4 different alcohols, and acetone as our potential solvents. And so we are allowing binary mixtures of solvents. So this gives us 28 possible combinations of solvents. Okay, so that's a relatively small space that we're working with. And we're trying to maximize the crystal yield in this case, allowing the maximum temperature at which we can start the crystallization to vary. And we want to look at solvent consumption. That's not an objective in this case. We're just looking at how it evolves. Okay, so here are some results here. So I'm showing on the left the crystal yield as a function of the initial temperature. So if I fix here the maximum temperature at 290, which means I cannot have cooling, I just have anti-solvent crystallization, I end up with a mixture of acetone and water as my solvent, and the yield, which is quite high, but you can see that as I allow the initial temperature to increase, I can increase my yield quite a lot. Okay. If I go beyond this value here, I then have a switch in what is the optimal solvent mixture, and this is because of the boiling point of acetone. Acetone being very volatile, beyond a certain temperature, I cannot use it anymore, and then I'm using ethanol and water instead. And interestingly, if I look at what happens on the right axis at solvent use, which is shown by these triangles here, so this is the triangle corresponding to each solution that I've got here, you can see that the solvent use decreases significantly as I'm increasing the temperature. Okay, so I've got a win-win here. I've got greater yield and lower solvent use as I go to higher temperatures. Okay, so you can see the benefits of looking again at molecular decisions and process decisions at the same time. Okay, and out of this, I'm also getting the specific composition of the solvent. So actually, each of those diamonds corresponds to different mixtures of acetone and water. So I'm looking at the components themselves and their proportions. Okay, so we illustrated a few of this example. I now want to move to a different example to look at some other aspects of computer-aided molecular and process design and how that can help to design better processes. So I'm going to look at organic Rankine fluid cycle fluids and the cycle itself. We're going to now explore a vast space of fluids. So from the 28 possibilities we had before, we're going to be looking at 58,000, so rather a big increase in scope. And so the algorithms we use here become even more important. I'll touch very briefly on this, and I'll talk about choosing performance metrics as well. So an organic Rankine cycle is a device through which we can recover low-grade heat. So we have a waste heat stream, which is typically at a fairly low temperature, but which still like to extract value from that waste heat. And so what we're going to do is we're going to add a bit of work to the system, and we want to recover additional work by recovering the energy in the waste heat stream. And for this, we need a cycle, and we need a fluid to go around that cycle. So we take this fluid from a liquid at a fairly low temperature. So this is the temperature entropy diagram here, so we're somewhere down here. And we're going to increase its pressure via a pump with the added work that we put in. We're then going to put this fluid in contact with our waste heat stream, and that's going to evaporate the fluid. And then we're going to recover the energy that the fluid has gained through a turbine, and that will give us the work output that we're looking for. Okay, so we're trying to add as little work here as possible to recover as much work as we can here, extracting heat from our fluid here. And we're then going to take our vapor stream here, that is now at a lower pressure, and we're going to put it in contact with a cold stream. And we're going to condense it back so it can go back around the circle. Okay. So as you can imagine, the performance of the system is very much dependent on the properties of the fluid itself. So we're going to take a system of 58,000 possible molecules, and we're going to try and develop this from the functional groups, so the atom groups that I was mentioning before. So we have here, for example, for a given cycle, we have here the different temperatures. So we have the lowest temperature at which we can operate, and we have here the medium or the highest temperature of our waste heat stream. And so we have to operate within this window here. So if you look at different molecules from the set of 58,000 molecules, you can see that of these three, ethene, butane, and octane, only butane crosses the operating window. And this will depend very much on the system, the particular waste heat stream that we have at our disposal. Okay, so within the 58,000 molecules, which ones are feasible or infeasible will depend on the context. So it turns out that over 99.5% of the molecules do not have the right properties. So actually, many of these 58,000 are wasted effort. But the set, it depends on the problem, so it changes all the time. So we can't reduce it a priori. So we're going to use an MINRP framework to address this problem. And I don't want to go into a lot of detail here. I'd be happy to answer questions about this. But if we have, what I want to say here is that we've added, compared to a traditional algorithm, we've added a few tests and modifications to enable those molecules to be screened and to enable the infeasible molecules to be eliminated and for the algorithm to succeed. And then the other thing to point out here, which I mentioned earlier, is that we are going to try different materials, but we're not going to try all 58,000 molecules. And that's really important because it really cuts down the cost of so let me show you some examples. So we're using the equation of states that I showed you earlier. We're using the MINRP framework. And here are a few case studies. So we're looking here at 3 different case studies where we have different waste heat streams. And so you can see our upper temperatures are different in all 3 cases. And the lower temperatures also vary. And you can see here that we have quite a wide range of temperatures. But in case study 3, we have a very narrow range of temperatures. And that is going to have an impact on what is feasible or not. Okay. Finally, in this case here, we're looking at maximizing the net power output from the system. And in this case here, where we have solar collectors, we're looking at maximizing thermal efficiency as our objective. Okay, so 2 different perspectives on these problems. So if we look at the space of feasible candidates for the 3 case studies, out of the 58, nearly 59,000, you can see we have different numbers of feasible molecules. Case study 2, which has the widest temperature range, has 263. But case study 3, which has the narrowest range, has only 26. And the other thing you can see is if you look at performance versus the rank of a molecule in each of the cases, you can see different behavior. So in cases 1 and 2, where we're trying to maximize the net power output, we can see that that really drops dramatically quite quickly from molecule to molecule. Okay, so these are all visible molecules. In case study 3, the first 10 molecules also give us similar performance, and then we have a big drop in performance for the other molecules. Okay. The other interesting thing we learn with these case studies is, in particular, with case study 3, so these are the top 10 molecules here that we found, is that if you look at the properties of those molecules, so you will see in the literature, for example, many examples where people say, oh, well, you need to find a molecule with a low heat capacity, you need to try and find a specific molecular weight or different behavior in terms of the critical pressure. Actually, the performance of the process from a thermal efficiency perspective is not so clearly related to these properties. So you really need to look at the process and not just at the properties. And this is shown in this graph here. So this shows you the deviation from average for the 26 feasible molecules of different properties, so density, heat vaporization, and so on. And you can see in each dot here represents a molecule, a feasible molecule. The red ones are the top 10, so they're the really good performance ones. And the solid one is the top molecule. And you can see that, for example, on the heat vaporization, yes, they're all less than average, but actually the best one is pretty average in its behavior here. And there is a little blue dot you can maybe see here, which has the lowest latent heat of vaporization, but doesn't perform so well. Okay, it's not a high performing. And so actually the solid one, the best one, is not exceptional in any way in its properties. It's pretty average. And so that really tells us we really need to distinguish between properties and molecules and processes. Okay. The next thing I want to say about this type of ORC systems is that you can start looking at different objective functions. So if we look at net power generation as well as the total cost of investment, okay, and so these are the details of the design, the groups that we use to make our molecules, you can start looking at, if you develop algorithms that can solve this problem, you can say, well, I'm trying to be in this corner. This is the inverse of net power generation, and this is the cost. So you want to have minimum cost and maximum power generation. So you want to be here. And this shows you what you can achieve here. All those red dots, the diamonds, is the best you can achieve. Okay, so we're developing algorithms that enable you to find these trade-off solutions, and then you can choose where you actually want to operate as a designer. Okay, so very briefly, I will conclude with an example where we're not using the equation of state because we're not able to predict the properties that we want with that equation of state here, but we're using quantum mechanics or experiments in the design loop. And really what we're getting from molecular design here is we're getting guidance for the experiments that we should be undertaking. And so we've been looking at this in the context of reaction solvents. Now, reactions are quite complex, and you can do many things to try and improve their performance. You can use different catalysts, you can change the operating conditions, you can change all sorts of things. But what is not always well understood is that the solvent, which is neutral participant, is not really a participant in the reaction, has a big impact on the kinetics of the reaction. So, for example, what Rankine showed in the late 19th centuries is that you can have a radical effect of the solvent on the reaction rate. So the Rankine reaction, this specific reaction here, is 20 times greater in acetonitrile than in toluene. Selectivity can change completely, say from acetone to 1,4-dioxane for this Williamson ether synthesis reaction. And you can have completely different impacts on the catalyst. So you can have a deactivation of a catalyst in acetone, but no deactivation whatsoever in dichloromethane. Okay, so the choice of solvent really matters. And it's quite complex to decide what is a good solvent for a reaction. So to try and guide that process and decide which experiments to carry out, we've developed a methodology similar to what I've shown you before. So we take a small number of initial solvents, which we build from our little molecular Lego here, and we then obtain the rate constant in specific solvents. And we do that either through quantum mechanical calculations or through experiments. And we do that for just a very few solvents. And then we build a surrogate model from this small data set. We then use this model in the kind of optimization that I've been describing so far. And we design the best solvent. We then, if we find a new solvent, we go back to test that this was indeed a good solvent. So we do the more accurate measurement or calculation, and we then update our surrogate model. And we go around this loop until we achieve convergence, and we can verify our final designs experimentally. So we've done this, for example, as a proof of concept for this Manchurian reaction here between phenazone bromide and pyridine, just to find out in which solvent is the reaction fastest. And so we've calculated here the rate constant by quantum mechanics. Don't want to go into the details of how we solve the problems, but we used a space of 40 functional groups, so that's about 1,300 potential molecules that we can use as solvents. And we started with a small set of solvents, but for which the rate constant varied by a couple of orders of magnitude. And then we set our optimization approach out on this. And at the end of a few iterations, we found nitromethane as a potential solvent that did better than acetonitrile. Now, if you know about this reaction, you'll know that you want to maximize the dielectric constant to maximize the reaction rate. But as it turns out, acetonitrile and nitromethane have pretty much exactly the same dielectric constant. So by going away from this qualitative assessment to a more quantitative assessment, we're able to identify that nitromethane allows a reaction to go faster. And we're also able to do this by evaluating only about 10 solvents quantum mechanically, as opposed to the 1,300 potential solvents in our design space. Okay? And just to mention also that we then carried out experiments in nitromethane and verified that indeed there is a 40% improvement in the reaction rate from acetonitrile to nitromethane. And the very last example I want to show is where we've put experiments in the loop. So we were looking at selectivity as well as rate constant for this SNAR reaction here. And so we were looking at the rate of this step here and the selectivity KO over KP here. And you can see that the selectivity is not related in any way to the dielectric constant. And there's also not so clear a trend with dielectric constant for the rate constant here. And so we developed this. And the nice thing about using optimization is that you can add other constraints. So we put constraints on the toxicity of the solvent, on the octanol water partition, safety constraints, on the flash point. And so you can integrate these different considerations into your design. And this is what we obtain. So we're looking to maximize the rate here on the vertical axis and to maximize the selectivity. So we want to be in this corner up here. Unfortunately, there is no solvent up here. So the best we can do are these open circles, which we identified for our optimization approach. And you can see that they are quite different molecular structures. Okay, so this is achieved with about 7 experiments, but all of the dots are different, different solvents that we can then go and try. So we can go and verify, for example, we verified that valerianide indeed has a performance that we predicted in this case. So to conclude, what I've hopefully shown you this afternoon is that by integrating molecular and process decisions, we can improve process performance in multiple objectives, taking into account the environment and safety aspects. But to do that, we need predictive structure property models, and they need to be able to predict the right properties. So for example, caloric properties were very important to be able to assess energetic costs. But we also need to tailor algorithms to overcome a lot of the complexity of changing the molecules as well as the process conditions. And I've shown you a few examples like crystallization, heat recovery, reactions of how this in practice can actually work. And I very much hope that we can make this work for the manufacturing of plastics as well. So I'd like to conclude by thanking the very many people who have contributed to this work. So these are all the students and postdocs in the group who have contributed to what I showed today, and my collaborators at Imperial and elsewhere, as well as our funders. And thank you very much for your attention. I think there are some questions, so I'll start answering those now. So the first question here is, how computationally viable is it to search for multi-component mixtures, so more than 2 components, for crystallization solvents or ORC fluids? And have I got any feel for whether much better solutions exist once you go beyond binary mixtures? So for crystallization solvents, we have gone up to 4 or 5 components, and we've never found anything with more than 3 components being better. So nothing with 4 components, 5 components, and so on. For ORC fluids, we have looked at up to binary mixtures, and you do get better performance with binary mixtures. So I think the main benefit comes from not necessarily an improvement in performance in, say, cost metric, because in fact using mixtures can add a lot of complexity, but it can have a big impact on things like the environment. So as more and more compounds are added to the, to reach this legislation and become illegal to use, then mixtures become more and more important, because you can use molecules that are relatively innocuous in order to get the performance that you need. So there are no other open questions. If you have more questions, I'm happy to answer them.
Hi, thank you very much, Claire. If anyone does have any more questions, then please do feel free to either email them, and we can send them over to Claire on the IMSE email address. So that's IMSE at imperial.ac.uk. So just going to say thank you very much to Claire for such an informative webinar. It was really great. Thank you so much. So a recording of this webinar will be put on the IMSE YouTube channel very soon. Oh, there does actually seem to, oh no, it's okay. Sorry. So a link for this, I put that in the chat function. So the next webinar in this series will be on the 16th of June at 2 p.m. So that's on the theme of making and breaking materials with ionic liquids, and it will be discussing designing solvents for producing more sustainable carbon fibers and for enhanced plastic recycling. And this will be presented by Dr. Adjiman Brandt-Talbot. Next week, we have a webinar in the Challenges in Antimicrobial Resistance webinar series, and that's going to be on Thursday, the 11th of June at 2 p.m. And Dr. Pavani Chakapali will discuss nanocomposite sponges and an emerging low-cost bacterial adhesive services. So thank you again, Claire, for the webinar, and I hope you all have a good day. Thank you.
Thank you. Thanks, Leah.